Dear students, in previous class we were discussing about the properties of Euler-Torsion functions. What is an Euler-Torsion function? We know that it is the Euler-Torsion function phi of n is the number of positive integers less than n and relatively prime string. Also we know that for any prime p and alpha greater than or equals 1, we have phi of p power alpha is p power alpha minus p power alpha minus 1. Also, if m and n are any two positive integers, suppose they have a common divisor d, then phi of mn equals, we have it is phi of m into phi of n into d by phi of d, where d be the GCD of this m and n. D is the GCD of this m and n. Now check whether, suppose m and n are relatively prime. What happens here? When m and n are relatively prime, we know that d is 1 here. Okay, instead of d here it is 1. When d is 1, we also know that phi of d, what is phi of d? Phi of 1. Phi of 1 is also 1. So for when n and n are relatively prime, then we have phi of mn equals phi of m into phi of n. So this can be proved from this result. Or in another way, without the help of this result, how can we prove it? Without the help of this result, we can prove when m and n are relatively prime. What about phi of mn? Phi of mn by mn equals, it is product p divides mn. Phi of mn equals mn into phi of mn by mn equals product p divides mn 1 minus 1 by p. Okay, why? Because we have phi of the product formula. We have the product formula phi of n equals n into product p divides n 1 minus 1 by p. So with the help of that argument, we know that phi of mn equals mn into product p divides mn 1 minus 1 by p. But since m and n are relatively prime, p divides mn means either this p divides m or this p divides n. But p doesn't divide both m and n. Why? Because m and n are relatively prime. So this product p divides mn 1 minus 1 by p can be rewritten as product p divides m 1 minus 1 by p into product p divides n 1 minus 1 by p. Okay, why? Because p divides mn, since p is a prime, then either p divides m or p divides n, but p doesn't divide both m and n. Why? Because m and n are relatively prime. So what is this? Phi of p divides m, product p divides m 1 minus 1 by p is nothing but phi of m by m. And the second term is nothing but phi of n by n. You can cancelling this m and n each other. So it is finally phi of mn equals phi of m into phi of n. So this is the another proof. Okay, right. So this is the third property of Euler-Torsion function. Now we are going to some another important property, that is when A divides B. If A divides B, then what is the behavior of phi of A and phi of B? That's our next task. If A divides B, then can you say that phi of A divides phi of B? That's an important result. It is true that is for any A divides B, for A and B are any two integers, positive integers, then phi of A divides phi of B. How to prove this result? So the proof is in this way. This is done by induction hypothesis. A divides B. A divides B means what is B? B is the product of or multiple of A. That is B equals AC. Okay. B equals AC. So by division algorithm, we have the C ranges from where to where? 1 to B. Enough. Okay. Now, first case, if C equals B, C ranges from 1 to B. So consider the first case if C equals B. When C equals B, from here what you get, what is A? When B equals AC implies, if C equals B, B equals AC implies A equals 1. Sure. Okay. So A equals 1. So what is phi of A? That means phi of A equals phi of 1. We know that phi of 1 is 1. Agree? That's a standard result. Also we know that 1 divides every integer. Since phi of B is an integer, so 1 divides phi of B. 1 divides phi of B. 1 divides every integer phi of B. Here instead of as 1 divides phi of B. But what is 1? 1 means phi of A. That means phi of A divides phi of B. So when C equals B, the result is true. Clear? Okay. Second case, if C less than B. If C less than B. If C equals B, then B equals AC should imply A equals 1. Means phi of A equals phi of 1. But phi of 1 is 1. 1 divides every integer. That means 1 divides phi of B. So phi, instead of 1, it is phi of A. So phi of A divides phi of B. If C less than B, what happens here? If C less than B, then B equals, A divides B means that gives B equals AC. Okay, B equals AC. Then, when B equals AC, what is phi of B? Phi of B equals phi of AC. Agreed? That means phi of B equals, since C less than B, and suppose A and C are not relatively prime, then phi of B equals phi of AC. What is phi of AC? It is phi of A into phi of C into D divided by phi of D. Where what is D? D is GCD of A and C. Okay, this is a proved result. When M and N are any two integers, we have phi of Mn equals phi of M into phi of N into D by phi of D. Where D be the GCD of M and N. Instead of M and N, here it is A and C. So phi of B is phi of A into phi of C into D by phi of D. What is D? D is GCD of A and C. Now use induction. Suppose this result is true for every integer. Suppose this result is true for every integer. True for every integer less than. Suppose this result is true for every integer less than B. Now, when B, before going to that one, first we prove that when B equals 1, what happens? That's again another argument. So before going to this one, let B equals 1, what happens? Let B equals 1. What is B? B equals AC. When B equals 1, since A and B are positive integers, they have only one possibility. A equals 1 and C equals 1. So when A equals 1 and C equals 1, and what is phi of A? Since phi of A equals 1, phi of A is phi of 1, that is 1. And what is C? Again, phi of C equals 1. Okay, phi of C equals 1. Since B equals 1, phi of B is also 1. Then we have 1 divides 1. That means phi of A divides phi of B. So the result is true for when B equals 1. Okay, for induction, the result is true for B equals 1. Now assume the result is true for every integer less than B. Okay. Now, every integer less than B means, what's our assumption? Or what's our second case? Our second case is C less than B. C less than B. And what is D? D is the GCD of A and C. D is the GCD of A and C means D must divide C. Okay, D divides C. When D divides C, it is true for every integer less than B. So when D divides C and it is true for phi of, assume phi of A divides phi of B. Let B equals 1, A equals 1. Now the result is true for B equals 1. I now assume that the result is true for every integer less than B. So means phi of A less than phi of B. means that this result is true for every integer less than b. Okay, right. Now c less than b, d divides c, then clearly this we have phi of d divides phi of c. Sure? Yes. So phi of d divides phi of c means what is phi of c? Phi of c equals some k into phi of b. K is an integer. K into phi of. Therefore, what is phi of b? Phi of b equals phi of a into phi of c. What is phi of c? K into phi of d into what remains? D by phi of d. Phi of d are cancelling each other. What remains? Equals k into d. K is an integer, d is an integer, k into d is also an integer. Suppose it is k1. So it is k1 into phi of a. Means phi of b equals k1 into phi of a. Phi of b equals k1 into phi of a means phi of a must divide phi of a. So the result is true for every integer b by induction hypothesis. Okay. So this is the another property of Euler-Torsion function, that is if a divides b, then phi of a divides phi of b. Agree? Okay. Now come to the another property, that means the phi of n is even. Phi of n is even for every n greater than or equals 3. Phi of n is even for every n greater than or equals 3. How to prove this one? Phi of n is even for every n greater than or equals 3. Let us n equals 2 power alpha, where alpha greater than 2 or alpha greater than or equals to. What is alpha? When alpha equals to, it is 4. So n greater than 3. Okay. So when n equals alpha, when alpha equals to, it is 4. N equals 4 means it is greater than 3. So our result is when phi of n is even for every n greater than or equals 3. What is phi of 3? When n equals 3, what is phi of 3? Phi of 3 means 1 and 2. So it is again even. Okay, phi of 3 means 2. So phi of 3 means 2. Why? Because the integers which is less than 3 and prime to 3 are 1 and 2. So clearly phi of 3 is 2. 2 is an even number. So when n equals 3, the result is 2. Now let n equals 2 power alpha. For alpha greater than or equals 2. For alpha greater than or equals 2, surely n greater than, strictly greater than 3 itself. Okay. So what is phi of n? Phi of n equals phi of 2 power alpha. Phi of 2 power alpha means, what is phi of p power alpha? We know that phi of p power alpha is p power alpha minus p power alpha minus 1. So here it is 2 power alpha minus 2 power alpha minus 1, where p is a prime, alpha greater than or equals 1. Okay. That equals 2 into 2 power alpha minus 1 minus 2 power alpha minus 2. So 2 into a number. Clearly, the multiple of 2 means it is even. So when 2 equals 2 power, when n equals 2 power alpha, where alpha greater than or equals 2, then clearly phi of n is even. When n equals 3, also phi of 3 is 2 means it is even. So phi of n is even for all n greater than or equals 3. Now, suppose this n has at least one odd prime factor. Suppose this n has at least one odd prime factor, let it be p. Then what is the product formula? By product formula, we have n equals, phi of n equals n into product p divided cn 1 minus 1 by p. Okay. So that means that equals n into product p divided cn, it is p minus 1 by p by taking LCM. Agreed. That equals n into product p divided cn p minus 1 divided by product p divided cn p. We know that product p divided cn of p is an integer, n is again an integer, so this n by product P divided this is nothing but some C of n into product P divides n P minus 1. Where the C of n is, what is C of n? It is n by product P divides n P. This is nothing but an integer. Okay, so clearly it is phi of n equals some. Now we have it is phi of n equals some integer, that will be C of n into product P divides n P minus 1. What is P? P is an order prime. So P minus 1 is always even. So this phi of n is also even. When this n has at least one order prime factor, then again we can show that this phi of n is even. Okay. Here we assume n has at least one order prime factor, let it be p. Now again we assume that suppose this n has r distinct prime factors. N has r distinct prime factors means this n can be written as p1 into etc. into pr. Suppose this n has r distinct prime factors. Each pi is a prime. What is pi? Pi is a prime, order prime, or pi is a prime. So what is pi minus 1? Pi minus 1 is always even. Therefore, what is this p1 minus 1 into etc. into pr minus 1? This is nothing but each of this product is a prime. P1 minus 1 is a prime, P2 minus 1 is a prime, P1 minus 1 is an integer, even, P2 minus 1 is an integer, it is even, etc. PR minus 1 is also an even. Why? Because each PA is an order prime. So it is some P1 minus 1 is even. So it is some 2 into K1, P2 minus 1, it is 2 into K2, etc. into it is 2 into Kr. That equals 2 power r into it is K1 etc. Kr. Okay. So it is 2 power r into K1 etc. Kr. That equals 2 power r into some K. Agreed. So what is phi of n? Phi of n equals before in the previous case we know that what is phi of n? Phi of n equals C of n into product P divides Cn. It is P minus 1. Agreed. So from there, phi of n equals C of n into, again, product P divides n. It is product P divides n. It is 2 power r into K into Py minus 1. Enough. So that means it is again 2 power r into K is an even. C of n is an integer. So it is nothing but phi of n is. So phi of n is always even when n greater than or equals 3. If n has at least one prime factor, that's immediate. If n has r distinct prime factors, then this can be proved by this way. n equals p1 etc. pr. Each pi is a prime. So each pi minus 1 is even. So p1 minus 1 etc. pr minus 1 are even. It is 2 power r into some k. Phi of n equals c of n into product p divides n. Instead of here, it is pi divides n. Product Pi divides n 2 power r k into Pi minus 1. It is again even. Okay. So these are the properties of Euler-Torsion functions.